All right, so let's get started. So one heads up is next week, Bison CTO will join us in the first hour to give us a 1 hour talk about like what Bison is doing, and then maybe they will release some opportunities for the intern. So if you guys are interested in, just welcome to join us. And the talk will be online, so you can just use a WebEx link to join us. Okay. Okay, so in the second hours, I will still take over and then to follow on our course. So yeah, this is our plan next week. Okay, so let me first quickly do a recall about the file system, because actually last time, I think there are some concepts I did not really describe that well. So I'll give you some examples later. So first of all is file, and the file is a linear array of bytes. I think it is quite simple. So each file has a low level name that uniquely identifies itself. So it is called an inode number. And then when the file is stored in the storage device, then it uses an inode number to identify the file. So it's not a file name, okay? And the second important thing is about the dictionary, because dictionary in Linux is just a special type of file. So actually, like if you create a dictionary in Linux, then that content will get a new inode to describe that directory. So each directory has an inode number as well. And here is a directory tree that you usually use in Linux. It always starts from the root. So here is a root, a backslash. And then it follows by several separators that, for example, if you are going to traverse from the root to the hide.txt, then the path will be backslash tmptem and backslash hide.txt. Okay. And files referred by the absolute path name, it should be from root. So from root, this path is an absolute path. Okay, so because like there's no really difference between the dictionaries and files, so like the directories and files, so actually you can have the same name, because name is not really matters in Linux, because directories and files, even they have the same name, but they can have different inode number. So it is possible to do the things like this. Okay, so also like there's no Linux doesn't care about the file extension. So like .txt, even you remove the .txt, it still works. Okay. So I think here is the more important things about the file descriptor part. So file descriptor is an integer to identify the open file in all file-related operations. Okay. So it's assigned by the kernel when a file is open and is valid only within a process. So different processes, they can have their own file descriptor. Okay, so let's look at an example on the right-hand side. Okay, so this is process A and this is process B. So you can also see in process A and process B, they all have the process descriptor starts from 0, 1, and 2. And usually file descriptor or FD 0, 1, and 2, it usually means input file, output file, and error file. So usually the first three file descriptors, they usually are saying about the same things. And after file FD2, like FD3 to maybe thousands of file descriptors, it depends. For example, process A, if it opens a file, then it can get a file descriptor. Okay. Okay. So usually two processes may use the same file descriptor, but it doesn't mean they are using the same file. You can think about like different process, they have their own process descriptor. So even they have the same number, it doesn't mean like things. Okay. So inode, each file has just one inode. So noting like file descriptor is the concept for the process. Okay. A process open a file, they get a file descriptor. But inode is not the same thing. Inode is for the file that really stored in the storage device. So even there is no process, open the file, there's still inode number, there's still file in your store device, right? So inode number is still there. Okay, so inode number it is not only a number because it also contains several metadata. For example, the access right, the date, the pointers to the file data, all these kind of things. Okay. Okay, so last time we said like actually there are several data structures here. There are process descriptor, sorry, there are file descriptors, there are inode table, and between them there are also open file table. So actually there is a question is about why we need all these three kind of like data structures here. Why not just merge them to one? Actually, it is possible to do it to merge them to one, but it will make the management become so complex. So here are some examples here. Okay, so the design of open file table is to relax the complexity of inode table and file descriptor table. Okay, so one more time, actually, it is possible to say like, let's split the rules of the open file tables into two parts. We can merge the first part related to the file descriptor to the file descriptor table, and the second part related to the inode table to the inode table. It is also possible, but here are several issues that we need to face. First, if process A and process B open the same file, in this example, FD0 in A, FD3 in B, for example, actually, FD0 here, and then FD3 is here, and you can see even these two, they point to different open file in the open file table, but actually they are opening the same things because they are from different process, so they get the different open file table entries. But both of these file descriptor, they point to the same inode 1976. Okay, so here the issue is like, actually for process A and process B, they own two different kind of file descriptor. That means like they have individual access mode and individual file offset. So what do I mean for individual access mode and individual file offset? Come to think about it, if one process opens a file with the read only and the other opens a file with write only, actually for inode, it doesn't really matter. I mean, for inode, it doesn't really know how many files are opening this file and in what kind of access right. So if we are going to move this management into the inode table, it will be super complex. Okay, so to make it simple, inode table only manage the like file on the storage, the things related to the data on the storage. So for this kind of processing information like access mode and file offset, actually they try to move them to another data structure called open file table. Okay, so let's go a little bit deeper. Like, for example, there is things called file offset, because if there are two processes or even there is the same process, they open the same files. And actually, for example, for the first process, maybe it is going to access the beginning of this file. But for the second process, it is going to access the tail of the file. Then actually, for the file, there is only have one file offset if they are pointed to the same open file table. Okay, so the thing is like this. If we only have the inode table, we don't have the open file table here, then we have two processes. They are going to access the head and the tail of the file. Then inode table cannot handle it, because usually for inode table, we can only store one offset. Just like we can only store the only position like the file is now accessing now. But if with open file table, we can realize this design. In this example, like FD0 and FD3, they are pointed to different entries in the open file table. So they can maintain their own file offset. So when process A is accessing FD0, the file system knows like, hey, actually, FD0 is now accessing maybe the head of the file. And the other one would be this one. When process B's FD3 is accessing the tail of this file, then when the operating system schedule for the process B for FD3, then once again, we can move the offset to the tail of this file. So with this information, even there are multiple processes that are sharing the same files, we can still manage the process level issue. Okay, And because there are several processes, they can share the same file. So there is a reference count to count about like how many files are now sharing this inode. Okay. So there's another thing is about the locking, because I saw there are several questions that are talking about the locking, about like when there is two files, they open the same, two processes open the same file, and process A and process B, they are going to write the data, write different data into the same file. Then there is a rest condition if we don't use locking, right? So usually there is a file lock, and there are a lot of ways to implement a lock. But the key idea is like this. Actually, the lock is not stored in the open file table or inode. So the lock system in Linux, there's another system called subsystem called lock systems. So when two processes, they are going to access the same file in the right operations, then, for example, process A, they're having like fd0, and fd0 needs to acquire the log from the log systems to write the data. So at the same time, actually, even process B's fd3, it is going to access the same, like inode, for example. It cannot do it because the file, the log now is now given to the fd0. So using this file descriptor table, a good way is about like in Linux, like the log is acquired in a granularity of file descriptor. So different process, even you are in the same process, you have different file descriptor, you still need to get the log before you are going to write the data to the file to avoid this kind of race condition issue. Okay. So there is another example is about the inheritance, because we say in Linux, like when process A forks process B, then process B shares most of the information of process A, including the file. So in this example, process A forks process B, for example, it will be look like this. The fd2, if you already in the process A, fd2 of both process A and process B, actually they pointed to the same open file table. So the reason is like the process A forks process B. So when the time the fork is finished, then process B fd2 is also pointing to the same entry in the open file table. So the same thing is like if like file B now, it needs to open the new one, or like it needs to do some update to this entry, then it will follow the copy on write issue. But the copy on write way. But if process B only reads the information, then it can just purely share with process A. Okay, so this is the way like how forking this kind of inheritance influence these structures. Okay, so let us for the file descriptor part. So let's move a little bit deep to the storage device. Okay, on the storage device, like we store the inode, and in addition to inode, we also store some other kind of informations here. So this is the directory tree. Here is a subdirectory from root. And then in the same label, there are subdirectory 1 and then the file 0. And then inside the subdirectory 0, there are also file 1 and file 2. So this directory trees looks complex, right? So in the storage device, how to reflect this kind of directory? And here's an example. Actually, the boot and super block, I think it is not very critical here, because boot and super block, usually they are going to describe, for example, which device we are going to use to boot the systems. Okay, so the boot block you will usually put in the device that we're going to boot. Usually is in maybe your SSD or hard disk drive. Okay, and the second one is super block. So super block is for each file system that has their own super block. So for example, if you have a disk and you are going to partition a disk into 2 partitions, but you're using different file systems, then on this device, you will have 2 super blocks. So 1 file system, 1 super block. So yeah. And then later on, there's inode tables. So inode table is going to maintain the information about the file, so including where the file is. So with this inode table, we can find where is the data block. Okay, for example, where is the file for file 1 in the storage device. Then we use the inode table to point to the address or location on the disk, so we can find, oh, actually it is on this locations. Okay, so I think the file part is quite intuitive, because file is just like data, so you put the file there, so it doesn't have too many kind of things to talk about. But directory is quite spatial, goes like this. Okay, so each directory, actually you can see like it is a directory block. So directory block is just like a data block, but the difference is about, in this kind of data block, they put in the directory entries inside. So we call them the directory block. But actually the things is very similar to the data block. I would say like it is the same things, but the difference is about the content inside the data block is different. So for directory block, actually we only put the directory entries inside, and the directory entries will look like this. So like this, this is the name of file 1, and then inode for is related to the file 1. So using these directory entries, it is possible to know like, hey, which file name can be linked with which inode. And using these entries, you can get the inode table in some places, and then you can get the content. Okay, so these directory entries, that, for example, for here, for subdirectory 0, because inside this directory there are 2 files here, so we will have 2 entries here. But come to think about, if you have another entries is 1 folder, then you will see the same things, like the folder name and the inode number for that folders. Okay, so this is how directory entries work like. Okay, so using these directory entries, actually you can do a recursive loop to get the whole directory tree. For example, if you start from the root, and you can go to find the child directory from the root, and then the child directory from the child directory. So you can go deeper and then to find out all the data in these file systems. Okay, so it all start from the root directory and checking the directory entries one by one. Okay, so this is a quick overview for the file system part. Actually, today we'll go deeper into about like, this is about the storage device. But when the CPU is going to access this information, actually, we'll move some of the information into the memory before we can access them. But what is the difference between the data in the memory and the different in the storage device? So, okay. So before that, let's give you a quick example. Last time, I think we start at the middle of the log structure file system. So I'll quickly go through the log structure file system. Okay, so the log structure file system, actually, it is designed to deal with the sequential access things. Because when we are going to write data in a sequential order, actually, it is not enough for hard disk drive, because hard disk drive usually it rotates all the time. So even we can write in a sequential way, but we cannot make sure how many processes are there writing the disk. Okay, so if there are multiple processes they are writing in the same sequential order, we still cannot make sure the data from the same process they are writing into the disk in the order they are predicted. So usually we need to issue a large number of contiguous write. So we need to group them together. So there is a concept, it's called write buffer, and write buffer is quite general usually. So we buffer all the objects in a memory segment and write a bunch of data to disk in a batch. So in this way, like this. Okay, so this is called a segment. So there are several data blocks, and then we have an inode to describe those data blocks, right? Because we need the inode to know where the block is. So if the data structure and the data is looking like this kind of format, and then we just group them in the write buffer, and then we will write into the hard disk drive in the same time, at the same times. So this is what we call a contiguous write. So if we are going to just write in a sequential order, you can think about like, we will first write DJ0, and then we will write DJ1 and DJ2 and DJ3, and then inode J. Okay, but the thing is about, if we write it one by one, but for example, if we first write DJ0 and then we stop for like 5 minutes, and we write another called DJ1. Then for this 5 minutes, actually hard disk drive already rotates to several kind of circles there. So it is hard to know if DJ1 can really place in the nearby of the DJ0. Okay, but if we group them together and then we run them in a batch at the same times, then we will force this information can be written in the hard disk drive in the sequential way. Okay, so this is the slight difference between the sequential write and then contiguous write. Okay, so because we can, with using the buffer and we contiguous write the data on the hard disk drive, in this way, actually, when we are going to access the data, for example, if we are going to access data J, DJ, then we'll first check the inode. And with this inode number, with this inode information, we can know where is the block address. So this is block address 0, 1, 2, 3. So it has, okay, it has like A0 to A4, A3, then we can get the data out. Okay, so the good thing is about if we read out this data continuously, because the physical limitation of the hard disk drive, it always rotate in the same directions. So those data can be read out at the same times. And in the memory, CPU will process the data. So CPU will know, oh, okay, so I know J here includes several data blocks, and we luckily already read them into the memory, so we don't need the second access here. Okay, so this is the concept about why we need this kind of log structure file system. Okay, but here's the question is, but how to find an inode in a disk? Because you can see now inode actually they separate across the hard disk drive, right? And we say if we can find an inode, then we can find the data. But how to find an inode? So this time we say like, actually in the old Unix file systems, they are put in the fixed locations. So when at the beginning, like we are going to partition the disk and then we are going to mount the file system on it, actually we will allocate a continuous space here and a space like A start here, and then before the A start, actually there are all for inode. So we put the inodes together at the bottom of the disk, or maybe at the head of the disk. So in this way, we can easily find where is the inode, right? Because if we only need to store the A start. With this A start, then plotting the offset of the inode size, actually we can know which inode it is. Okay, so in this way, in this old Unix file system way, we can easily get the data and inode. But the thing is about, that means like for every access, we need to access 2 locations on the disk. One is about the inode location, another is about data location. So the access latency will be twice for getting 1 data. Okay. Okay, so a better way is about why not just move the inode and data together? Because inode 1 is for data 1, inode 2 is for data 2. We already know these things. So if we can put inode J with DJ and inode K with DK, actually luckily if we access the inode J, then actually the head of the disk can also read out the following data. It doesn't really need to jump to other locations. So in this way, the performance can be like only need half of the time we can get the data out. Okay. However, inodes now are scattered, so we cannot get an inode. So now we use another new data structure called inode map. So inode map, actually you can think about like, this is a summary of several inodes. So like this, inode 0 to J means like we are going to summarize the information of inode 0 to inode J, those J plus 1 information here. So for example, inode 0, inode 1, inode J, they are placing like AX, AY, and A4, those locations. So with reading inode map, we can actually get where the inode is. Okay. So using the inode map, we can get inode, and using the inode, we can get the data out. Okay, but the same question is about like with using the inode map, yes, we can quickly identify a batch of the inodes, but how about inode map? So we still need a non-fixed location to know the inode map. So in the log structure file system, we will use this checkpoint region. We put at the very beginning of the hard disk drive. So this checkpoint region, you can think about is another summarize of the inode map. Okay, so for this summarize, actually for inode map 0 to j, it will point to imap 0 to j, and it starts from A5. Okay, so with this, we can make the checkpoint region super small because the checkpoint region is the data for summarize the inode map, and inode map is a summarize for inode. Okay, so this is how the log file system used to get the data. First of all, you need to get the checkpoint region, and usually because the checkpoint region is super small, so checkpoint region usually they would be put into the memory. So actually, we only need to care about where is the inode map and where is the inode. So actually, we can get a faster access time compared with the old Unix file systems. Okay. Okay. So there is an example to let you know about what about the directories. So I think from now here there will be a new stuff that were not included last week, the past 2 weeks, I think. So we have inode map, inode directory, inode and directory here. Okay. So like this, a directory is just a collection of name, inode number, and mappings. So a directory like a file has their own inode. So there are the things you already know. So in this example, if inside the inode map, there are 2 different kind of inode. One is for directory and one is for the data itself. So with parsing inode map, actually we can know actually the first directory we can get from A3 here. So this is for the directory. So it should be /home. And for A1 here is for the test, the data about the test. So it is on A1. Okay. So with using inode map, we can look at 2 different kind of inodes. And one is for directory and one is for the file. So for the directory inode, actually we can get the data according to the inode number from here. And then for getting the directory data, actually we can use the directory inode to get it. And for getting the data, we can use the data inode to get the data. Okay, so like this. Okay, but here comes an issue. If we are going to update test, or if we are going to update the data, so data here is DJ. So after updating the data, actually we need to move to like DJ here, a new data here. Okay. And because the data is moved to the new DJ, the reason like DJ needs to place it in another direction, another position is because maybe after accessing DJ becomes larger. So when DJ becomes larger here, we cannot directly in place update the data here. Okay, so if DJ becomes larger, then we need to find another place to put it. Okay, so you can think about we will, according to log structure file system, we'll put into the tail of this hard disk drive. So maybe it's here, DJ. And because the location of DJ is updated, so the corresponding inode should also be updated, right? Because inside the inode, there will maintain the block address information. So now the DJ is moved to A5, then inode J here will update the block address to A5. Okay, and because the inode J is updated, so the inode map should also be updated, right? Because inode map inside it is now pointed to say like, hey, actually, data J is now at the inode of data J is now at A1, but actually it is now updated to A6. So IMAP will be updated again to point it to the A6 for inode J. Okay. Okay, but what will happen if there is no inode map? Okay, it will be like this. Because we say, hey, actually, we have inode directory and inode j here. Okay, and they're all the same things. Inode directory will point to the directory data, and inode j will point to the data itself. So, okay. So if we do the same thing, we update the data, update the text. So data is called DJ. So after update, we will put the DJ at the tail. There are same things for the upper. So then after that, we need to update the inode j. Okay, but the thing is about actually, if we update inode j here, then the directory entry should also be updated, because the directory entry will point it to the inode data for itself, because test is under directory entries here. So when test is updated to other place, then D directory should be also updated. Okay, so like this, we need to also update the D directory to a new place to say like, hey, actually test J, or sorry, the data test is already moved to the new place. Okay. And the same thing is because we update the directory, so the inode directory should also be updated. Okay. So if there's no inode map to help to summarize the inode informations, if only there's inode, then when we update the data in some place, then we need to also update all the parent directory from this path. So there will be a recursive update here. Okay. So the recursive update problems will affect the parents, and then you will cause a performance issue here. So inode map, not only like using the inode map, we can also rely on the checkpoint region. So the checkpoint region can put into the memory for the fast check-in. This is one of the advantage. The other advantage is with using this inode map, actually we can avoid this kind of recursive update problem for updating the directory. For updating the data if it is on a deep directory. Okay, so this is some kind of things to let you know for a low structure file system stuff. Okay. Okay, so I think file system will stop here because actually different file system, they have different designs. So it is hard to go into detail for each of the file systems. And low structure file system is the very basic file systems. I think you can think about like this. Most of the well-known file system now, they will adopt some of the concepts from the low structure file system. Okay, but because like there are a lot of different file systems in our like no matter Linux or Windows, actually you can choose about you're going to use the NTFS or like you are going to use for the ext4 or like exFAT. So there are a lot of options there. So it is hard for the programmers to like send different kind of requests for different file system, right? I mean, if you are a programmer, then if in your systems there are 10 file systems, so you need to write your code in 10 different ways. Just want to communicate with this file system. So it is, I would say like it is inefficient, but it is still possible. So actually, virtual file system is coming to solve this problem. Is it possible to virtualize the functions for most of the file system? For example, actually, for different file system, usually they have the read operation, they have the write operation, they have delete, they have the directory create. We can also remove the directory. So those of the general function, actually, they share across the file systems. So if we can abstract those kind of functions by things called virtual file system, then we only need one code to manage all these kind of file system. I mean, virtual file system will help you to take care. For example, if one user now is going to interact with the virtual file systems, then if the virtual file system know actually this user A is going to access like ext4, then virtual file system will help to translate the code for compatible with the ext4. So virtual file system can help you to manage this kind of complexity to make the programmers don't really need to deal with different kind of file systems. Okay, so like the goal for the virtual file system is to enable programs to use standard Unix system code to work regardless of the file system or underlying physical medium. So you can think about, for most of the programmers, they will think, actually, no matter they are using NTFS, ext4, exFAT, or like those kind of stuff, actually they looks very similar, or even there's no difference between them. And this is because there is a virtual file system between the programmer and the file systems. If there is no virtual file system, then each programmer should handle different way. For example, maybe the parameters, for the read functions for different kind of file systems, maybe the parameters numbers will be different. For example, for ext4, maybe for ext4 you need like 4 parameters for the read, but maybe for like exFAT, maybe you only need 3 parameters. So you need to rewrite your code to follow this different kind of file system. But now virtual file system help you to deal with this kind of stuff. Okay, so this is the reason why we are going to give you some brief, I would say like brief knowledge about the virtual file system. Okay, actually like with the virtual file system and block IO layer, there are all the abstraction layers. So abstractions layer is just the most objective for the abstractions layer is to let the programmers feel very simple to program, to control this kind of like device and file systems, because they don't really need to worry about, actually there are different kind of device, there are different kind of file system, they need to write different kind of code. They only need to use one I would say like standard library. They can control all this kind of stuff. Okay. So the thing will be like this. Actually, for user space, most of the users, they only know read, write, like make directory, this kind of functions. But actually, system in the operating system, virtual file system will hook the right system code with the system write, this kind of virtual file system function. And for this virtual file system function, actually, this one will hook to all different kind of file systems. For example, for exFAT, they have their own implementation for write method. And maybe for ext4, ext3, ext2, they all have different implementations for the write. And VFS will help to hook all these kind of file system together. Okay, so this is about the virtual file system. So actually, after you learn virtual file system, actually you will have a very, I would say like, will have a very concrete concept about how file system is designed. Because virtual file system will include all of the key design for file system. Otherwise, it cannot really be simple to hook with all different kind of file systems. Okay. So because like virtual file system already be developed for like several decades here. So at the very first version of the virtual file system, it refers to the ext2 file systems. Okay, so ext2 is very classic and very old file systems. And the VFS as an abstract layer, I mean, the design of the VFS is referred to this ext2. And also most of the new file system, they also share very similar points with the ext2. I mean, there are differences, but because most of the concept, they are start from the ext2. Like ext3, ext family, they share the same concept for the ext2. And also like different exFAT and NTFS, they also use similar idea from ext2. So actually, VFS, most of the data structures, most of the interface, they are from ext2. Okay. Okay. So actually, for VFS, here are some mapping between the data structure inside the memory and on the storage. And this is what I mentioned in the first few slides about. Actually, in this slides, we only talk about what data look inside the storage device, right? But when the data is read into the memory, it will be a little bit different. Okay. So actually for VFS, there are 4 primary object types, or you can think about there are 4 very critical data structures here. So the first one is superblock object. So superblock object represents a specific mounted file systems. So as we mentioned before, for each file system, you get one superblock. So if on one disk you have 10 file systems, then you need 10 superblocks on that disk. Okay. And the second one will be inode. So inode object is to represent a specific file on the storage device. Okay. And the third one will be the entries object. So it represents a directory entry, which is a single component of the path. Okay. Oh, sorry. Let me give you an example for the entries. So because if you have a path /user/home/temp, and for this path, actually you will have 4 D entries. One is for temp, one is for home, one is for user, and one is for the root, because you have 4 layers. So the VFS will parse it and then break to 4 D entries objects. So for each of the component, it will get 1 D entry object. The entry object for the root, the entry object for the user, for the home, for the temp. And file object, actually, it is to represent an open file as associated with a process. So today we'll focus on the middle, inode and D entries. The reason is actually file is just about using the file descriptor and then to do some things. And the superblock, actually, it is about when you mount the file system and what information do you need. And the key thing is about, so how about how inode and D entries, they work together? Okay. Okay, so I think this one is super important. So let me rephrase again. The VFS treats directories as normal files. So there is not a specific directory object here because they are all managed by the inode. Okay, it is inode, not D entries. I'll talk about what is D entries about. But D entries is not purely for directory entry. D entries is usually for the fast lookup for looking up where is the data in what kind of directory. So it doesn't really mean this is directory entries. Okay. Okay. So after talking about the data structure, there's another important thing is about the things called operations. So operations is more like when we talk about objects, object is like a data structure, like the data structure for inode, the data structure for superblock, the data structure for D entries, right? But how about, for example, if we are going to create a new inode, if we are going to remove a directory, if we are going to use a hard link, if we are going to create a soft link, then how to implement this kind of algorithm? So they are all included in the operations. So operations you can think about is the algorithm that are going to do some things. Okay. Okay, so like this. There are a lot of operations. There are super operations, inode operation, the entries operation, file operations. So I think actually even that looks like a lot, and maybe there are a lot of noisy words here, but you can think about like this. Actually, they are talking about very similar concept. It's about we need some methods to manage file system. Then it is super operations. For example, if we are going to sync the file system, if you are going to create the file system, if you are going to destroy the file systems, then those methods, how to implement it, then it is about a super operation. And here is one interesting thing is actually using these operations. For example, if now we are going to deal with ext4 and xfs, because there are 2 different kind of file system here. So each file system will show their own operation implementation. For example, for ext4 and xfs, they both have remove directory, but maybe their logic is quite different from each other. So the operations will help to point to the remove directory functions implemented by ext4 and xfs. So when you are using the ext4, then operations for remove directory will use a pointer to point to the code for ext4. And now if you are going to use the XFS, then the pointer will point it to the function for XFS. So these operations, they are all defined by different file systems. Okay. So we'll give you more kind of examples later to tell you about, to give you more kind of feelings about what this kind of operations look like. Okay. So first of all, let's start from a very, I think, basic concept is about the superblock object. So superblock object is designed to store information describing the file system. So when mounted, a file system invokes allocate-super. So this will raise a superblock of the disk and fills it in the superblock object. Okay, so usually when we are talking about blah, blah, blah object, VFS object, superblock object, D-entries object, those kind of objects, they are all the data structure inside the memory. Okay, not on the storage. They're all about the memory data structures here. Okay, because you see here, like read is superblock of the disk. So we already have a superblock of the disk, right? Because when at the very beginning, like you're going to partition the disk and you are going to mount it a file system on the disk, and at that time you already put a superblock in the disk. Okay, but when you are going to use this file system, you need to read this kind of superblock data to the memory to then becomes a superblock superblock object. So the data structure in memory will look like this kind of stuff. Actually, there are a lot, but I'm just going to show you a very important thing is inside this object, inside this data structure, actually there is a pointer. This super operations. So these operations will point to the operations that relate to the superblock like this. So this one, S dash operation will point to all different operations or like functions supported by the superblock. So superblocks operation can get which specific operations according to the superblock, and then using this pointer, we can point into these operations. And then for each kind of the rotate inode, dirty inode, write inode, drop inode, this one can also be hooked by different file system. So each file system has their own write inode, like drop inode or delete inode way. Then this hook can be hooked to different file system. Okay, because we are now using a virtual file system, so actually we need a real file system specific under this file system, under this virtual file system. And the implementation for this file system will be directly hooked with this virtual file system operation stuff. Okay, so I think let's take a 10 and then come back later.对啊，还有小时，对，看一下。小时。
我想问一下，这个 example two 是什么意思啊？
就是 Project B 继承了 Project A 的档案，因为你 Project A 如果 fork Project B 的话，它的 file descriptor 这张 table 会直接复制出来。
我看一下哦，就是，
但这个 example 并不是这样画的，只是刚刚好是拿这个同一个 FD2来做 example 而已。就如果实际上这个 Project A 是复制的，fork Project B 的话，整张是跟 Project A 会一样。
哦，
对。
所以
这只是给
上是不一样的 process。
对。
但是他们只到同一个 open file
的可能性，其中的可能性这个。
哦，就是，
但它还有很多其他可能性啊，只是其他可能性我觉得比较实，所以我就没有放上来了。
哦，那就是一个 file system 只会有一个这个东西嘛？
只会有一个这个东西，对。
还是这个形态的东西有很多个？
应该说一个 disk 上面可以有很多个这样子的东西，然后一个档案系统确实它就是大概就长这样子。
哦，因为我在想啊，就是比如说，我这个 directory entry 下面假设还有 directory， 它不是也会有 directory 自己的 inode 吗？
对啊。
然后它不是还要再回 inode table 才能再继续这样？哦，
所以很大。
哦，
对。
再看一下。哦， 所以这个跟这个差别只是在于有没有 IMAP 来
对，
找
有没有辅助而已。
哦
对，如果没有的话，基本上它就是还要知道说这个 directory 它的 file 在什么地方，这样。
所以上面这个是比较好的。
就是上面那个是比较快的，
哦，然后我看一下
就它把 directory 跟 data 资料分开来管理。
哦，
对
哦好，
对，
然后我看一下哦，嗯，就老师你刚刚说你说不同的 file system 它有不同的这个实做这些
对
function 的方式嘛，
对
然后你说是每一个 file system 都有这个，只是实做方式不一样的意思吗？
我觉得应该是说每个 file system 里面它有自己各自的这些 functions，当然它不一定每个都会对应到，
哦
就是有可能 A file system 可能就没有某一个 function，也是有可能的。对，
哦，
但是它这个是可以透过就是 function pointer 去知道你想要的那个 file system 的实作方式，所以它这个只是个抽象的，就是它并没有真的完整的实作在里面。所以它的实作是要去 link 到你底下包线怎么去做实作，它等于是 summarize 这样的 interface 出来给这些包线去做复刻。对
哦，
对，因为它是抽象层，所以抽象层本来就不
所以这
会有
个是在 virtual file system 里面的。
就是在 virtual box 上看到我会有这些 interface 可以做使用，然后这每个 interface 对应到就是它会可以互回到不同的 file system 的实作。
哦，所以
对
就是如果你要做一个新的 file system，它就先去读它的 super block。
应该说你要去就是宣告一个新的 file system 的话，或者是你可能今天开机你要去存取的 file system 的话，那你就是要把它所有 block 资料全读出来。
哦，然后再把它放到 memory 里面这样。
对
哦，所以一台机器可以有很多个 file system。
对，没错。
那
甚至比如说一台机械，一个 disk 都会有很多个 file system。
哦哦，那我们现在用的，比如说很正常的一些 disk 是只有一个吗？
没有啊，就看你怎么用。你也可以把一个 disk 里面就帮你的 C 槽、D 槽都可以放。
哦，
对，
好好，谢谢。
先
那问那个啊，这样的话，它如果你前面的 PPT 有 I know map 了没有？就有一条了没？那在前面，这个哦，
这个 sorry，
就是它如果像后面它不是都已经有 I know map，然后说有固定位置是只去那边，那它干嘛还要 I know table？它每个 I know 不都分开？那 I know table 意义在哪里？因为它有
我懂你的意思了。应该这样说，iNode table 这边只是个示意图，但是你的 iNode 的资讯就是这里。
然后实际是分散的。
对，就是它这个 iNode 其实就是这个 iNode table 里面的东西，就是这里的 iNode 讲的就是
I know table，
就是 iNode table。对，只是在这边的时候，因为如果乱画的话，大家可能会太
东西都很
对，
乱。
所以我就把它放在一起，就跟大家说，反正就基本它就是一个属于 iNode 的资料结构。对。但是它至于它到底是在一起还是分开的，那就是看它后面这个地方，它实际上在地上面是怎么去做实做的。对，
所以基本上应该都是，其实你刚才说最后呢，就是它有一个固定，然后只去 I know me，然后 I know me 就指向前面。
就是我觉得应该是说最 basic 是这样做，但是如果一些比较新的 file system，它可能就不一定这样做，因为毕竟这个是最标准的做法是这样子。对，但是
它固定的那一块是只有一块，
就是对，就是当初的设计就是固定那块只有一块。对，但是你如果说今天如果你存档案非常多的时候，它也是可以就是有2块3块。对，
反正就是会有，
反正就是会有固定的区域。对，就是它一定要有一个固定的位置是知道起始点是什么地方。对对对对，
谢谢。
谢谢。
想请问，iMap 它这样改完之后，它会马上去改这个东西吗？
他会马上去改这个东西。我想一下啊，会。
那这里说的它就是一段时间更新一次，
就是这里的话，我觉得应该是分成这样说，就是这里我想一下哦。还好。好，这我回去查一下，但我觉得他应该要马上更新才不会出错。
也感觉
对。
那我还想问，就是这个，就是如果没有 iMap 的话，它不是要所有跟它有关的
对
更新？
对。
那怎么找到？就是我怎么知道我改了这个？那我到底有哪些人需要跟着改？
你说你怎么知道你
上面
你上面有谁？就是它其实会有，就是 iNode 里面它会有往上跟往下，对对对，的空位它可以去上下这样查找，对对对，这样
我想问，为什么这边会有这样 recursive update buffer？
因为这只来2个而已，但是如果它一层有很多的话，那就一直往上改到它的根节点，对吧？因为它这边是去记录说，就是 DJ 是存在 D 的 r e 这里面，可是如果
通常 parsing 只是最后一台开始 parsing。
通常是对吧？我觉得要看你怎么想的问题，就是因为你现在改的最后一层，所以它当然是往回这样走这样子，对。但你如果改中间某一层的话，那就是从某一层开始再往上走。
老师，你说的 update 是其中某一个资料夹有改，
对啊，
它前面的就是都要改。
对，它前面都改，就是我觉得应该这样讲，就是它这个原因是因为这个 D 改了之后，它的大小会变，但大小变的话就没办法变在同个地方，它就要写到别的地方去。所以今天假设你的资料是没有变为止的，就是你这边还是可以写 A0的话，那就是不用改。对，
主要是资料大小的问题。
对，就是它如果你写完之后它变比较大的话，那它就需要做修改。
可是 iNode 不是不会乘大小？
可是这是 data，
哦，还是档案？
对啊，对，它是档案。
哦，好，谢谢老师。
谢谢。
我先改一下那个，
好，
我刚刚才
非常好。跟刚才同一个名字吗？我看到了。
不知道哎。
哎，
我那个
口试啊，我知道。可是你现在是口后试哎。
我刚刚是3对，
我把你变后试了，这样可以吗？哦，知道了，这样。好，不好意思。
他请问这个这2个方式
对啊，不好意思，我刚才这个其实只是说，假设他今天 process A 是 for process B，但是这个地方不是这样的？因为他如果 A 或 for B 的话，是整个 process table 会整个复制出来。
哦，
对，但是因为地址不够，我想说就直接用这个，只是想跟大家说，其实像这种 FD2 会知道同样的东西，通常是因为是 fork 造成的。对，对。
然后他后面会再
就是它会只让同一个，因为它是直接复制档案，复制 process，所以它的 file descriptor 是直接会知道同一个 open file table。对，那
多个 process 也是这样子。
对，就是你每个 for 它就会全部知道同一个地方来，
嗯，
就是你 for 几次，它就全部知道同一个地方。那这个地方是 open file table 是要有 open，它才会创一个新的 entry 出来。那像 for 它没有 open，所以它没有创新的出来。对，谢谢。
这总是2个。
好，那你可以开吗？好，现在好像没了。
另外一个没了。
好，那这条
现在我可能要，
那我来。好，我帮你开一下。等一下哦。咦？嗯，有了。这样，看可以吧？
有。
好，下。
就我想问那个，就是那个刚刚讲调整后哪里？哦，就是刚刚讲的这一页讲 DN3 object 的时候，我有点搞不太清楚。
这个等下会有比较具体的讲，就是 D entry 它比较特别，它其实不是代表 directory entry 的复制，因为 directory entry 到时候大家会看到它其实都是从 inode 的 object 去做修改的。D entry 的用意其实是让我们做快速查找去做使用的。就你今天如果要找一个档案的话，那因为我们通常都是从 root 开始这样一个找下来。
对
，D entry 是用来维护这个输送结构去用的。所以它通常跟底下 storage 的结构是，它不会去修改底下 storage 结构。对， 等一下会有一个比较具体的
所以它
example，
跟这个也不太，它跟这个 directory
它是利用这个去建出来，但是它是一个有点像是它把这个，因为它这个地方这样子来讲的话，它并没有把 path 直接建出来，
嗯，
因为它是本来就存在上面嘛，所以它只是知道说，哎，谁领到谁，谁领到谁，谁领到谁。
对，它没有
那
关
the entry 它是比较像说可以把这个 path 这件事情把它建在 memory 里面，然后让我们去做查询的时候可以更快去做查询。
所以一个 directory 它会有 inode object 之后，但是它不会有 dentry object，我可以这样理解吗？一个 directory
没有，第一个 directory entry 都会有 inode 跟 the entry， 只是它来控制，就是通常可以这样想，就是你今天 remove directory 或者是 make directory 的时候，它是通过 inode 去做控制的。那 d entry 只是拿来做加速用的，就是 d entry 其实是一个比较像是加速用的资料结构，它跟这个 directory entry 上面存的资料是不会修改它的，通常不会修改它。对，会修改它的就是你建一个资料夹，你去删一个资料夹，它其实是用 inode 去控制的。对，因为这个就会回到，因为本来在 Linux 里面 directory file 就是同样的事情，
对，
所以它都是用 inode 去控制。对，那 d entry 这件事情是为了要我们赶快要去查找说，哎，我这个档案是在哪个资料夹里面的时候，它要快速去查找的时候，会透过 d entry 去做快速的定位。对，所以你可以想象成 d entry 比较像是记录那个 path 的那些事情。对
像这个 directory entry 这边 storage 存的就只是说我的前一个或后一个是谁，但是它没有把完整的连起来之后，但是 d entry 有，它可以把一个就是有点像 directory 的结构建出来。
我那个 clarify 一下，这边其实存的就只有这个目录底下的资讯而已。
对，我知道，
对，所以它只会连到它的上一个，那下一个是不会有的。
好，
对，就这里面的下一个，它基本上不会记的。然后 d entries 会把它在 memory 里面把它建出这个关系。
有点像一个是建一个，我可以想成一个是建 parent 跟 child 关系，然后另外一个是建整棵树。
对
，OK，
类似这种感觉。
OK，好，谢谢。
对。All right. So let's come back. So first of all, let me clarify. Actually, this example 2 is not about like actually process A and process B. In this example, there are different processes. So actually, what I'm referring is about if process A forks process B. Actually, the file descriptor table will be the same. Will be totally the same if process A forks process B. Okay, but in this example, I'm just going to show you for FD2, because for FD2 here and FD2 here, they point to the same open file table. There are several reasons to lead to this kind of result, but one of the most general way is about to use fork. Okay, so example 2 here and process A and process B here, I would say it's not really the same things, because now process A, the file descriptor for process A is not the same as process B. So in this example on the right hand side now, it's not about process A forks process B. Okay, but because I have no room to draw another figure here, so for example 2, you can think about actually when there are two file descriptor, they point to the same open file table. One possible and general reasons is about maybe it's because these two processes, they are fork relations. One parent fork the child, so their file descriptor pointing to the same open file table. Okay. So that is for the clarification. And okay. Okay, so for super block operations, actually it's going to perform the low level operation on the file system and its inodes. So if a file system wants to write to its super block, actually it can like this. Super block point to the s dash operation, the pointer point to the super block, and then to write the like super block operation like this. So this is about here. You can use this. Sorry, one more time. So you can use this super block to point to the operations. And in the operations format, you can choose one of the functions you are going to run. And in this example, if we are going to write the super block, for example, to write something into this super block, then we will use this write dash super block functions. So it depends. If you are going to delete inode or you are going to write an inode, then you will use this chain from the super block, get the super block operations and do the operations. Okay. And here are several things. The first one is about like allocate dash inode is to create and initialize a new inode object. And then destroy is about to deallocate. So the creations of inode actually depends on the file system. So it is from the super dash operations, we will do this kind of stuff. Okay. And here are dirty and write. So dirty and write, you can think about dirty is about when an inode is dirty. So you can use this function to do journal updates. Okay, what is journal updates? So dirty means like when there is a file and you move the file into a memory and you modify the file in the memory, and if you are going to write back to the storage device, then one way is called journal. So we will write the new data from the memory back to the storage in the journal area, and this is how to manage this kind of dirty inode. Okay. So write dash inode is going to write a given inode to disk. Okay. And then delete inode is about just to delete the given inode from disk. Okay. So put dash super is going to code when unmounted to release the given super block. Okay. And this one, write dash super is to update the undid super block. So because these data structures, they are in the memory. So this super block data structure is in the memory. So when you call the super dash operation inside this write dash super, we can synchronize the modified information from the memory to the disk. So it is about the synchronization usage. Okay. Oh, one more time. Actually, like in your final exam, I mean, I will not really ask you about like what this function is about. I mean, actually, these functions here just want to let you know what super block operations look like. Just give you some feelings. So they will not be on your exams about to ask you about, for example, what is put dash super means and what is sync dash fs means. So the same things for all the rest of the like inode object operations, those kind of stuff. There will not be all on your text about what each of the meaning of each functions. Cool. Because I think this is too tedious. Okay, so that is for super block. So the next one, I think the most important thing is the inode object. So inode object represents all the information needed by the kernel to manipulate a file. So this inode represents metadata of each file on the file system, and the inode object is constructed in memory only as files are accessed. So inode is usually on the disk, and inode object usually it is in the memory. Okay, so you can think about inode is a file backup version for the inode object. Okay, so here are several kind of inode operations. So this operation here is just want to let you feel about like what is inode objects, what is the rule of the inode objects. So like here we have a create. Create is to create a new inode associated with the D entry object with the access mode. So here are several parameters that you can use to create a new inode. And here is a kind of lookup. Lookup is quite important. I mean, we'll give a brief example about how lookup affects the file lookup. Okay. So lookup here actually is about to look up a certain file in this file directory tree. So we search a directory for an inode corresponding to a file name specified in the given D entries. So as you already know, file name is stored inside the D entry. So given the D entry, we can know the file name. And we will use the file name to trace the tree about to get where is the location of this file. So there will be an example later, like how to parse the absolute path to get to the end of this data. And also there is symbolic link, like creates a symbolic name link and names sim name to the file. So because when you are using a symbolic link, you can think about you are going to make a kind of extension from one file, right? So this shortcut, this extension, this shortcut, actually you can give it different names. It doesn't really need to be the same names as the original file. So the same things here, the SYM name here is just going to let you know, actually, when you are doing the shortcut, actually you can give it different names. Okay. Okay. So there is another thing is called remove directory. So one important thing to let you know is about, actually, even now we are talking about inode, but because we say in Linux, directory and inode, sorry, directory and file, they all use the inode, right? So inside the inode operation, actually, there is make directory and remove directory. So inode can control both the status of directory and file. So make directory, remove directory, and then rename, they're all about relationship between the directory part. Okay. So actually the rename function is very, I would say like, it's quite special for you guys like to know, because rename, maybe when we are using the Windows or like using the Linux, actually, if you are not using a command line, the rename is just about you really type the name of the file and you type a new name, right? But actually in the implementation of Linux, it is not really to directly modify the name inside the D entry. Because when you are using the command line, when you are going to rename a file in Linux, actually there is no rename function because you need to move the file from one name to another name, right? The way you are going to rename the file in Linux command line, you will say, you will use a MV instructions or like the MV command to move the file from one name to another name. Okay, so in Linux, actually, it moves the files specified by old entry from the like old dir directly to the new dir directly. So actually, one to make it short, it is about we need to replace the old D entry by the new D entry. We are not going to directly modify the name inside the D entry because there will be some consistent issues. And I have an animation later to let you know what would happen if we directly modify the name inside the D entry. Okay. So the next one is the D entry object. So the entry object is about the hierarchical nature of the file system. Like for this example, like we have a path like /home/hello/world, right? So actually we'll get 4 D entry objects /home, hello, and world. Okay, so actually when we are going to store this kind of information on disk, each of them we can receive a directory entry, right? But only using this directory entry, it will be time consuming to construct the path. So to read all this directory entry from the disk to the memory, actually we use another object called the entry object to quickly find out, to link out this path together. And then always can use this path, or like a virtual file system can use this path to quickly locate where is the data is. Then this one will give you an example about how to kind of parse this kind of path name and how to get the data out later. Okay, so I think this is also quite important. The VFS constructs the entry objects on the fly as needed when performing directory operations. So the entry object does not correspond to any sort of on-disk data structure. What does it mean? Like this. When we are talking about inode object, actually we said inode object, there is a file backup in the storage device, right? Because inside the storage there is inode table. So inside the inode table, we maintain both directory and file together. And inode object is going to describe those file and directory. But the entry is not the same things, because the entry is not going to describe how the data stored inside the storage device. The entry is about how to quickly find out the path. Given this path /home/hello/world, is it possible to quickly know where the location is without accessing the storage device. Okay, so the entry object is for the optimization for finding the data inside the memory, not from the storage. And we'll let you know later, like how does it work. So usually the entry object can be in one of the 3 states. The first one is the U state. So U state is corresponding to a valid inode and is owned by some users. I think this is quite common, just like if there are some process and we're going to read out the data from the storage device. And of course, like when you are going to read out the data, you need to first parse the path name, right? You need to know where the data is. So you need to first parse the path and then get the data. So you need both the entry and then the inode object. Okay, so there is another state is called unused. So unused is about the entry corresponding to a valid inode. Again, for that data, there is a file path, but the thing is but it does not belong to any user. Maybe the users already released the file, but because those files are still in the patch cache or like in the memory. So for short benefit, for example, if maybe this file is a hard file. So in this case, we will choose not to directly release the entry objects at the moment the user released the file. So this is the things I say, it just cached there. In this unused state, no process use this kind of the entries. Okay. So there is another thing is called negative. So negative is not associated with inode. So either the inode was deleted or the path name was never correct. Okay, so this one is because even the path name is not correct or the inode was deleted, we still put the entry, we still put the path name inside the memory. Is because if one day there's another process open the same file, then in this case, we don't really need to reconstruct the path again. Because as we mentioned in the prior slides, the entry is just for the optimization for the fast accessing the file path. Okay, so for fast accessing a file path, it doesn't really need to be consistent with the storage device. Okay, so this is for the negative state. So both the entry objects and the corresponding inodes can be cached for faster directory lookup and file metadata access. Okay, and this one I'll give you one example later. So let's quickly look into what the entry objects look like. Okay, so actually this is the entry objects related kind of operations. So I'm just only to talk about the D-hash. So D-hash, it looks like to create a hash value from the given D entry. And the VFS codes this whenever it adds a D entry to the hash table. So like, because it is very time consuming if we are going to compare the entry one by one, right? Because the entry you can think about is a string. Then we are going to compare it. It takes a lot of time. And a better way is if we can hash the string to some hash number, then we can directly compare the hash number. We can know whether these two the entries is the same or not the same. So using hashing, we can quickly know like if the this the entry already exists in the memory or not. Okay, so this is I think this is how hashing can benefit this kind of data finding things. And the rest of them, just like the entry release, the entry delete, or input like this, I will just skip it because I think it's not quite important. So okay, let me directly jump into the key things because I think I know the entry, it is not easy to understand. So let me use the rename to make you an example about how those kind of information look like. So in Linux, actually, rename function, it works like to replace the old the entry with a new one, having a new name. Okay. So I think there is a very intuitive question is about why not just directly modify the name in the D entry? Why we need to create a new D entry and replace the old one? It seems like it takes a further step to to realize this rename process, rename function. But there are there are a lot of reasons, but just these two reasons, I think they are better to understand. The first one is consistency issue. And the reason is because updating the name directory directly is not atomic. So like this. So this is for reason one's example. So this figure is just like our prior slides. So in our storage device, there are several regions. One is for inode, and one is for data blocks, and one is for the data blocks, right? So inside the derivative entries, inside the derivative block, there are several derivative entries belonging to that directory. Okay, so these are all the same as the prior. So inside the memory, actually, you can see there is a D entry. So this D entry maintains about the information for file one's information. So because inside the D entry, there is a file name and there is an inode pointer. So this pointer will point it to the corresponding inode. So here, the inode object for the file one can use the inode pointer in the entry to get it. Okay, so inside the inode object, actually there are several information. So this is a stat. So stat means about if this file is updated or not. Is it a latest version? So if the stats say, hey, actually this is a dirty file, it means the file is updated. And it doesn't consist with the storage part. So it becomes dirty. So clean means like in the memory and the storage, the data is consistent. Okay. Then the second one is the file size. Okay. So because the file size, it varies. I mean, we don't really limit the size of the file. So some files is large, some files is small. So the inode will describe about the size, about how large it is. Okay. And oh, sorry, there's a typo here. This should be operations. But this operation, just like you already know, like inode operations. So we can use this operation to point to any kind of inode operations there that we are going to use. Okay. And then the last one I think is quite important is a data pointer, because this data pointer will point to the data in the page cache. Okay. So when we are going to access the file, in this example, this file is called file one. So file one will be moved. I mean, the data block of file one will be moved to the memory, and it will be placed in the region called page cache. So you can see actually both data structure and page cache, they all use the memory. Okay, but the difference is about like if we are going to get the data in the page cache, then we need the pointer inside the inode object. So this inode object can help to point to where the data is stored in the memory. Okay. Oh, one another thing to let you know is actually in the inode in the storage device, there is also a pointer to point to the location inside the storage device. So in the inode object, the data pointer is pointing to the memory address. In the storage device, the inode is going to point to the block address inside the storage device. So this is quite different for these two data structure. Even they look very similar, but the pointer points to different place. Okay. Okay, so this one is just to let you have a big picture about like what is a D entry and inode, and then we are talking about page cache at the end of this lecture. Okay, but probably maybe later or maybe next week. So okay, the thing is about if we are going to update the name for file one, so if we directly update the name in the D entry, then we need to do next step is to update the name inside the directory entries, right? Because we update the name is inside the memory, but we still want the update to be shown inside the storage device. Otherwise, you shut down your computer and you reboot it, then the file name will be inconsistent. So we always need to sync with the data in the storage device. Okay, but the problem is here. If we are going to directly modify the file name, and when the virtual file system starts to write back the updated file name to the directory entries on the storage device, but if there is a power failure, then we will face the partial results inside the directory entries, right? Because for example, if the file one's name is quite long, and maybe we will need to write several characters inside the directory entries, then we face a maybe system crash or power crash. Then in in this case, the data, the new name inside the directory entries will be partial, and there will be an error. There will be an inconsistency here. And the reason is about when we are going to write the data in a storage device, it should take a super long time because storage device is so slow. So it makes these operations cannot be atomic. So atomic means about like these operations will not be affected by any crashes. Like we can make sure this operation is all or nothing. Either we can make the operation succeed or it will fail. Okay, but updating the name into the store device is not atomic. I'll show you later what is called atomic. Okay, so a correct way is we will create a new D entries in the memory, and then we will give it a new name. So now files one's new name is here. And the inode pointer will still point to the same inode object because we do not really update the inode object here. We only update the name. And then we will write the entry back to the directory entries. Okay, we'll update the whole directory entries. And this can be an atomic operation because it can be all or nothing. Either we update successfully, otherwise we can roll back. Okay, we can roll back to the old version. Okay, because we will only we will create a new the entry, and then after we finish the creation, we will delete the prior one. Okay, so even there is a power failure, even we only write half of the new entry, it doesn't really matter. We can still roll back to the prior version. Okay, so there are only two steps. One is we do not really successfully update the name. Like we can use the prior old name, or we can use a new name. So there is no inconsistent state, or you can think about there is no unpredictable result. The result will only be success or failure. And if failure, you can use the old one. You can use the old name. But if you directly modify the file name here, if you directly modify file name, then there will be a ton of cases there because maybe you only write only 2 words or maybe 3 words or 4 words. So you cannot predict the results if there is a failure there. Okay, so this is how atomic is so important for this kind of file system structure. So this is the first reason. And actually there is another reason here. So another reason is if the new name is longer than the old one, and there is no space in the block, how does it handle? So you can think about like this. For directory entry on a storage device, the structure looks like this. There is inode number, and the inode number will be 4 bytes. And this is the static size for the inode numbers. Okay, so there is another thing called name-len. So this is 1 byte. Okay, so this is about to show how long is the len, how long is a name, because name is a variable things. For example, different files they have different length for the name. So we need to first know like what is the length for this name. So there is a 1 byte here, and there is a type. Okay, so like directory or not directory, something like that. So there's also another 1 byte. And then following on, we will put the name inside this directory. So usually we'll align the size of the name to the 4 byte. And actually we can have the maximum 255 byte here. Okay, so your name can be up to 255 bytes. Okay, maybe you have one question is about why not 256, right? Because 256 can be aligned with 4 bytes, but 255 cannot. So the reason for 255 here is because this example, like I targeted on, is on ext4, and because ext4 is a quite recent file system, and for the prior version like ext2, this kind of version, actually they limited the maximum length to the 255 byte. So it is about for the compatibility. So for ext4, we can only use 255 byte. Okay, but if now you really store a file and the name is in the 255 byte, then ext4 file system will help to pad 1 byte we'll have to pad like 0 data here to make the name to align with the 4-byte. So actually ext4 will help you to pad to 256 byte here. Okay, but according to the compatibility, you can still only use up to 255 bytes. Okay, but the problem is here, like the dirty entries will keep going on if there are new dirty entries comes, right? Okay, but if we directly modify the name, and if the name is larger than the prior one, so it means like if you directly update it, we will overwrite the other dirty entries, and it causes an error here. Okay, because you directly modify it, and the name here is already maybe, for example, it's 4-byte, but maybe after you update the name, it becomes like 8 bytes. So 8 bytes will become so large, and then we'll override the neighbor dirty entries. Then it causes an error. So this is another reason why we don't really update the name in the dirty entry. So if you create a new one, then you just need to mark the prior one as an invalid. Then we can avoid this kind of overwriting neighboring issues. Okay, so this is an example to let you know about how rename happens and what issues will you face about if you directly update the name inside the dirty entries. Okay, so this is for it. Questions? Okay, no questions. Okay. Second example is about the next one is about to let you know about how to access a file path. So usually a user process will request a file like this kind of format. I'm going to get the data from /path/to/file. Okay. So but how system process this kind of stuff? So step 1, VFS parse to get /path/to/file or components. Okay. And then VFS will start to resolve the path for each component. The first step is to check whether the entry of the component is 16 or not. Okay, because like this, if the entry, sorry, I think this one can be better. So if the entry is already in the memory, then we can use their inode pointer to get the inode object and the data pointer to get the data in the patch cache. Then we are finished, right? So it will be super fast. Okay, but the thing is about if not, okay. If not, then VFS will call the inode operations, the lookup operation in inode to search path inode from disk and create the entry. So this search path inode from disk, actually there are 2 parts. The first one is to let you know is here. This is the lookup. Oh, sorry, this is not a lookup function. Okay, here, sorry. The second build here, this is the lookup function. So inode will call this lookup function to get where is the data. And then because according to our example, we say we will search the path inode from the disk. So either this. Oh, sorry. One thing to let you know, the root directory inode is always preloaded during the system build. So this one will already be inside the memory. So for the root, we can always skip it. So the second one will be path. So this is the reason why we say to search path, not search root. So for the path inode, what we are going to use is like this. Here, when we are going to search the inode from the disk, we will usually follow this structure, like to get the checkpoint region and then to get the inode map and get inode, and we can get the data inside the data block. So either this is a dirty block or data block, we can use this flow to get the data. Okay, so this one is if the not pass. If this is not, then we'll do this kind of stuff. Okay, so we will recursively run the lookup function to resolve to and file. So at the end, we can know, okay, where is the direction of the file? Okay, so using this, first we'll search for the root, and because root already in the memory, so we'll use the inode for the root to point to the data block, to point to the data block. And because the data block stores the directory entries, so inside the directory, there should be a path. So reading out the path, then we'll do the same things. We will check about if the path, if the entry of the path is already in the memory or not. If it is there, then we can use the entry to find the inode number, to find the inode object, and inode object can find the data. But if not, then we will run this kind of operation, lookup operation, to search the inode from the disk. So either it is in the memory or it will be on the disk. Okay, so doing this in a loop, then we can finally get where is the data. Okay, so this is about how to put those kind of inode, the entry, and VFS operation together to access the data from the storage device or memory. Okay. Okay, so actually, there's one missing pieces that I did not really point out in the prior, is the file object, because I think actually the file object is not quite important. So I just give you a very rough concept about the entry and inode first. So the last one, because we say VFS, there are 4 components. The last one will be the file objects. So it represents a file opened by a process. So there may have multiple file objects for the same file, but each file has only one inode and one D entry. Okay, so file is the concept related to the process, because multiple processes can open the same file. So it is possible to have several files, just like the file descriptor layer. But inode and D entry, you always have one. Okay. And like the D entry object, the file object does not correspond to any on-disk data, because this data structure is corresponding to the process. So it is not really related to the inode, the data on the storage device. So when we are going to update the data, we always will link back to the inode object, and then we will modify the data on the disk like this. Okay, so like file system can implement unique functions for each of those operations, or they can use a generic method if one exists. Okay, so here are several hook points, like read, write, asynchronous IO read, asynchronous IO write. So actually, most of the file system that support this kind of function. So this function will be hooked to the implementation of different kind of file systems. Then we can the programmer can call the VFS, and then the VFS will help to translate to the corresponding file system stuff. So this, for example, let's read things like it read count bytes from the given file at position offset into the buffer. So the offset is the offset you here in the open file table. Sorry, it's here. The offset is here. So there are a very similar concept to think together. Okay. Okay, but I think details are not quite important. Just need to know like each process has their own file object, but actually, no matter how many processes to share the same file, actually they only have one inode. Okay. So if we quickly put the file system components all together, then you can see like this. If you still remember, each process has their own text structure, because text structure is like process control block. And inside a text structure, actually there is a field. If you go back to our, I think it's lecture 1, something like that, like there is a field called files. And actually using the files, you can get a file descriptor table, and you can get your corresponding file descriptor for the file you are going to access for that process. So this is a file descriptor table, and like for any file descriptor, like we will point to the file. So this is the file object. So here are several field here. So inside the file object, actually there are 2 things. It points to the file inode and also point to the D entry. So for the file object, actually we can get the D entry and the inode here. So those are all data structure inside the memory. Okay. And also there is a mount things, like the mount thing is about to describe this file is stored on which file systems. So this is a VFS mount. So to tell you about like where is the super block you need to find to get a file. And also super block, actually, we need a path to know where the super block is. So there is a de-entry stuff here. Okay, so this is just a like very brief architecture about it that you know the file system where they put together the virtual file system will look like this kind of stuff. Okay, so still have some time. Let me move to the patch cache. So one more time, back to this figure. Actually, we already learned about the block IO layer, those kind of stuff, and virtual file system we have. And actually, FS specific, you can think about this is the log structure file system part it is, but actually different file system here, they will have different implementation, but we skip this part. So we'll move on to this one, patch cache, because this one is quite important. When you are going to read the data block from the storage to a memory, you should put into the patch cache. Okay, so the maintenance for patch cache is quite important. So a patch cache is a disk cache. It is going to minimize the disk I/O by storing data in the main memory. Okay, so this is the file in a storage device, and then this is a memory. So in current Linux systems, the memory is managed by the patch label, right? But in storage, actually, it is about the block label. So there is a translation between the block and the file. So actually, this makes the patch cache becomes a little bit complex in the Linux code because like in the memory, we should use patch to manage, but in the storage, it is not about patch. Usually it's about a file and a blocks. Okay. So like this is the patch cache, and then for the read operations, so you can think about if there is a user process and we are going to read the data out. So the same things like if the user process send the read operations to the systems, then we need to call the system call because we are going to access the storage device. So for any operation, we are going to touch the storage device, access the storage device, we should always call the system call. Okay, so system call CPU will jump into the kernel mode to execute the kernel function. It's about check patch cache. Okay, so with using the check patch cache, CPU can also use a read patch. Okay, so it means like actually CPU will, in most cases, CPU will first check the patch cache. Unless you say you don't need to check the patch cache, but or in most cases, CPU will first check the patch cache because it is faster. So if it is hit in a patch cache, then data is in the patch cache. Okay. Oh, one more thing is about actually this patch cache is different from CPU cache. I mean, there are several very similar things because the people were talking about like LRU or like how to replacement, this kind of stuff. CPU cache is a hardware cache. So we use a hardware, we use a circuit to implement this cache. But patch cache is a software cache. You use a program to write this patch cache. So this is very different. Okay. CPU cache should be super fast because it is inside the CPU. So if CPU cache, I mean, if the operation of CPU cache is too slow, then CPU will stall there to wait for the cache to read the data. So CPU cache, the implementation of CPU cache should be not too complex, or for sure, it should be simple. Otherwise, if the circuit is so complex, then CPU should wait there for a lot of time. On the other hand, patch cache is a software solution. So usually it doesn't need to be so efficient like the CPU cache. So for patch cache, you can have more management, more control inside. Okay, so this is a difference between like the cache, because actually there are a ton of cache in this computer system. There are CPU cache, there are patch cache. Inside the storage device, there are also the buffer cache. And then in the storage device itself, there are also another cache. So there are all different kind of cache, but it depends on where the cache is in and how the cache is implemented. Is it a hardware cache or is it a software cache? Okay. So if it is cache miss, then data is not in a patch cache. Then it means like the data should be in the storage device. So we'll read out data from the storage device. Okay. So when we are saying like we are going to move the data from storage device to the patch cache, we will say like we are going to populate the data. So it's just kind of a terminology. I think it's not quite important. And then if we are going to write back the data from the memory to the storage, we call it evictions. So remixing is going to remove the patch from the cache to make room for more patch cache, because usually patch cache will eat up the memory. So the more patch cache, the larger it is, then you will need to sacrifice more kind of memory. So one interesting thing is about like patch cache is only for the file data. So if you still remember when we talk about the process, right? We have like heap, we have stack, those kind of things. Heap and stack, they also use the same memory. So if you have too large of the patch cache, so you will squeeze the room for like heap, okay? Because they are sharing the same memory. So the larger a patch cache is, you cannot use, for example, like mmap if you use too many, or if you use the memory allocation function, those for the heap usage, you cannot use too many because your patch cache is so large. Okay, so the size of patch cache is also one important thing. Okay, so to make room, actually, there's a way called ARU. I think you guys already know about it. And actually in Linux doesn't use the ARU. And ARU, you can think about ARU is a concept. And if you are going to realize the ARU implementation, it will be time consuming. So usually, no matter in CPU cache or patch cache, they don't use ARU. They use like pseudo ARU. Pseudo ARU means like their implementation is very similar to ARU, but it doesn't strictly the same as ARU. So this is the reason why in CPU we use like set associative, this kind of cache design. And in patch cache, we use Linux 2 this design. So they are all very similar to ARU, but not exactly the same, because if you are going to use this ARU to implement them, it will be time consuming. Okay, so I think maybe we can stop here and then let's come back next week. And one reminder is next week for the first hour, like we will invite Bison CTOs to give us a talk. So you guys can be here or can be online. And for the next 1 hour, we will follow on the patch cache. Yep. So thank you guys. Have a good day.
Direct entry 跟 D entry 是一个东西，是一样的东西吗？
不一样，
不一样。
就是 direct entry 比较像是你那个资料夹的组成是什么。D entry 在意的是那个 pen。
所以 direct entry 它可以知道下面的 inode 跟 file name 那些有的没的，的意思吗？
就是对，就是 direct entry 比较像是在储存装置上面要储存 direct 这个概念所需要的。可是 D entry 它的概念是要加速 path 的查找。所以今天如果你要管理 directory 的话，通常你不会用 D entry， 就 D entry 只能快速帮你定位到，哎，你这个还有 path 有没有存在，然后你要读档案的话要读哪个 object。所以今天如果要建资料夹、删资料夹，它其实是在 inode 里面去做这件事情。
哦，
因为 inode 是 file 跟 directory 是共用的。对，所以 directory entry、D entry 稍微不太一样，因为这个观念会关系到 D entry 是一个。它是一个没有一定要存在的资料结构，它跟 inode object 不一样。inode object 是因为你 inode 要操作一定要有个对象操作，所以 inode object 必须存在。但 D entry 是为了加速而出来的。你如果要快速找到某一个档案的话，你想要知道今天我给你一个 path， 你要怎么快速找到？你是靠 D entry 是快速找到，但你也可以不要用 D entry， 你就一个一个从 disk 里面读 directory entry， 一个一个键也可以。
哦，对啊，对啊，我原本以为是哦，所以 D entry 就只是存那个 path 而已，
还有一些就是连到哪个 inode object 去这种感觉。
哦，所以那我想问一下，这张图就是 D entry 只会出现在 memory 里面的意思吗？
对，对，
然后
因为它是 memory 的资料结构，就像 inode object 也只会出现在 memory 里面。
哦，
对，
好，然后还有下一个问题是这个，看一下，
好，我被我盖住了，
对，大家我调一下
还是我那边？
，OK 啊。就那张大图，我有一个问题，就是它这边是指有一些，就是假设这边是一个 process，
对，
然后它有很多
对
开启很多档案，然后它会先，就是这个的意思是 file 里面有这些那个
对
对，有这些 field， 然后它的这边 D entry 就是存它在的那个位置的意思，这个
对，
我刚刚那个哦，
那个档案的位置。对
哦，然后 inode 就是存这个 file 的一些资讯什么的，
对，
哦，那它所以 它的 path 这边还会存它是用什么 file system
对
的意思？
对吧？
哦
因为他要知道他这个 file 是放在什么哪一个。
那为什么它会指这个又指这个？这是什么意思？我不知道它这两个箭头是什么意思。
我觉得他这个箭头只是在跟大家说，它其实是可以 S 到 D entry 的，就是因为你要知道它 root 在什么地方之类的，所以它需要有那个路径。所以最后来说 D entry 它是不一定要有，就是你这边拿掉，其他都可以动。
哦，
但你要快速的去就是定位说，哎，V 就是 super block 在什么地方之类的，
哦，
那你就需要透过这个 D entry 的去拿到。
所以这里就是只知道它的 super block 跟一些 operation 之类的吗？是这个意思吗？
然后 super block，然后 operation 是透过它这边画，它这边应该还有一个 S dash operation 去指导 operation。
哦，好
对
好，所以 inode 也可以找到它的 super block，
对对，没错。
所以这个 file 可以从 inode 这边找到，也可以从这个
对
mountain
其实
找到。
其实上课讲的是比较简略，它这个是比较完整，就是说它其实都可以互通。
哦，
对，
好好，谢谢。
老师，我想问一下，就是这边说它的说2倍慢是跟这个比起来，是跟这个比，就是跟这个直接去拿，
对，
资料比起来比较慢。
对，2倍。
好，那因为我想问，它这里就是怎么去切，就是我有点不太清楚这个 body system 的。
怎么去切的嘛？就是比方说，因为今天我拿的时候，我先去看你这边底下有没有，那它底下大小其实就是比较小的大小。那如果底下都没有的话，例如我找到这个4的话，代表它是总共是2的4次方 block 加起来的大小。就它这个地方指的是这么大的一块区域，它4代表是2的4次方 block 加在一起的大小。就是2的4次方 continuous piece of patches，所以这边代表的是16个 patch 的大小。可是因为我的 request 可能不需要这么多，那我就把它下放到下一层区，然后下一层区我只会留一半，那我觉得再把剩下一半再往下面丢，所以我就会往下去做移动。反正就是我也是只留一半，我都会多要，但是我只会留一半下来。像这个2的4次方，你把它丢一半下去是2的3次方。对，它就会把2的4次方拿出来，然后分一半。
哦，所以是它如果没有用到这么大的空间，它就往下丢。
对，它就会把一直往下丢到你，等到你可以的时候，它就会把那个你要部分给你，然后剩下就留下来。下一个人如果要的话，这边拿啦，这边扫描就发现，哎，2的3次方它本来就有了，因为它刚才没有分完的。对。
哦，那那它这里的结构是什么意思？就是有大到小吗？还是？
这个应该是这样说，就是 cache step 跟 play， 对，它应该算大到小，然后 step 基本上就是以资料结构为单位去看的，然后好几个资料结构放在一起，它就变成一个 cache 这样子，就是一个 cache block 这样的感觉。对，然后这个 slab 就是一个资料结构，那因为一个资料结构可能有很多个 patch，对，对啊，就像这边的这种，
所以它意思是说，就是 cache 是用 slab 组成，然后 slab 是用 page 组成这样子吗？
对，等一下我看一下哦。对对，
好，谢老师。
没有，可以再讲是这个回声问题。
回声万这边的意思是说，如果你今天要把这个档案名称直接在 D entry 直接做修改，那因为修改完是在记忆体，所以你要跟 disk 去做同步。可是你这个同步的话，基本上它需要时间，因为这是 disk，所以你要写回来要花时间。因为跟 CPU 比 disk 很慢。那你花时间的时候，如果你今天会学的话怎么办？它就会直接可能写到一半而已。就例如它可能有10个字，它只加2个字，它就断电了。那在 SD 或者 hard 里面，它就只有2个字，那剩下8个字就看不到。
了解。
但是你复电的时候，它就只剩2个字，然后你前面的这个 name 也被你删掉了，因为你要先删掉，然后把它写。对，所以它如果只修改 name 的话，就会这个问题。
好，了解，谢谢。
哎，不好意思，我觉得我们转一下阵地，因为下个 slide 了。